Okay, so I want to do a series of lectures on projective geometry because I think it's a fascinating form of geometry that really sort of is more fundamental than many of the other things which we consider, like Euclidean geometry or hyperbolic geometry. I think it all begins really with projective geometry. And it's a subject which isn't really taught that much anymore in undergraduate mathematics, for example. But there are some remarkably beautiful facts in it and some really interesting lessons to be learned. So I'm going to start today with a discussion of perspective drawing. And later on, we're going to see how many other areas projective geometry touches. And it's really quite remarkable that this subject spans such a wide area. I mean, there are some interesting theorems from the ancient Greeks which touched upon projective geometry. I mean, some of the problems are very sort of geometric and all to do with straight edge constructions, and some of the problems turn out to be closely related to some really interesting things in topology, like how can we represent particular surfaces. So I'm going to start today with a discussion of perspective drawing. So perspective drawing is a technique which allows one to make pictures of 3D scenes which look very realistic. And one way to do perspective drawing is to get a canvas which is nearly transparent, and then to stand behind the canvas and then just to draw the outlines of the different shapes as you see them through the canvas. So that will tend to make very realistic drawings. So for example, we could think about what a perspective drawing artist would make of these railroad tracks. And of course they would produce a picture which would be very, very similar to this one that we see here. So here we have a very simple model of what goes on with perspective drawing. So this green plane here, this represents the scene, the kind of thing that the artist wants to draw. And on the scene we have these two parallel lines, which in this case are going directly away from the artist. So we think of the artist as looking at the scene from this red sphere here, which we're going to call the viewing point. So if you like, we can think of this as where the artist's eyes are. And these particular black lines, if we were thinking about picture before, these might represent the railroad tracks. Anyway, we'll label them L1 and L2. Now, this blue plane here, this is going to, in reality, be a semi-transparent canvas, and the artist is going to be viewing the scene through the canvas, and then they're going to be making marks on the canvas where they see the objects through it. So we call this canvas the picture plane. So here I've illustrated these two lines on the picture plane. And these are essentially the images of these lines on the scene, L1 and L2. If you like, you could think of them as the depictions of the railroad tracks. And if you look carefully at this picture, you should see that these two lines are actually sort of coming closer to each other. And if you imagine extending lines L1 and L2 further so that they go a very long distance away in the scene, then perhaps you can imagine how these two lines on the picture plane are actually going to converge. Now, what I want to convince you of is that indeed the images of these two lines are going to converge, and in particular they're going to converge at a very special point. We denote this point as V, and we call it the principal vanishing point. So we can describe this point in several ways. Firstly, if we have any two parallel lines which are perpendicular to a picture plane and go on indefinitely in the scene, then the images of those lines are always going to meet at this principal vanishing point. That's one way we can define it. Another way we can describe this vanishing point is if you start at the viewing point C and then you draw a line from C towards the picture plane, which is perpendicular to the picture plane, then V is actually going to be the place where that line ends up meeting the picture plane. So now I want to try and prove, or at least give a semi-rigorous demonstration that indeed the projections of these lines will end up meeting at this principal vanishing point. So in order to demonstrate that the projections of these lines, L1 and L2, do indeed meet at this vanishing point V, I've drawn an extra feature on this diagram. In particular, I've drawn these two purple planes, one corresponding to L1 and one corresponding to L2. So let me describe the plane corresponding to L1 for a start. I mean, actually, they're both similarly defined, but let's start with this one corresponding to L1. So this is the unique plane which passes through the line L1, contains the line L1, and also contains the viewing point C. Okay, so there's some important things to notice about this plane. So obviously this plane contains the viewing point C, I've just said that. But another thing one should notice about it is that since it contains the line L, which is perpendicular to the picture plane, that means that this purple plane here must also be perpendicular to the picture plane. And what that means is that this plane must in fact contain this line between C and V. So what we're saying here is that when L1 is sort of infinitely long, this purple plane here will actually end up containing this line between C and V, and hence the sort of most distant points of the line L1 are going to end up getting projected onto a point on the picture plane which is essentially very close to or equal to the principal vanishing point V. Now, we just made that argument for the line L1, but we can make an exactly analogous argument for the line L2. We can again define a plane which sort of cuts through L1 and cuts through L2 and contains C, and we can think about how that plane is going to be perpendicular to a picture plane and how it's going to contain that line between C and V. And again, we're going to get exactly the same conclusion, that plane cuts through V, at least it does when L2 is indefinitely long, and in that case, it's going to touch the vanishing point V, and therefore there is also a distant point on the line L2, which gets projected to the vanishing point V. And so this demonstrates that these two parallel lines on the scene are going to end up reaching a common vanishing point, which is essentially at the same height as the viewing point. Okay then, so now we're going to try and demonstrate something a lot more important. We're going to try and show that in perspective drawing, every single pair of lines which are parallel in the scene will meet somewhere on the horizon. Now, when I say the horizon, that has another name. It's also called the vanishing line, and we can define it exactly as the horizontal line which passes through the principal vanishing point. So, if you like, to find the vanishing line, you just draw a line out of the viewing point C, which hits the picture plane perpendicular to it, and then once you've done that, you draw a line which is parallel to the scene, which goes through the picture plane and goes through the vanishing point V, and you get this vanishing line, little v. So this is essentially the horizon, acts as a horizon in perspective drawing, and we claim that every single pair of parallel lines are going to have their images meeting somewhere on the horizon. Now, to demonstrate this, we're going to use a pretty similar technique to before, although it's a little bit more complicated. So, in particular, let's consider one of these lines, say L1. So we're going to assume that this line L1 goes on indefinitely. And we're going to consider the plane, which is the planar region, which is defined by this line L1 and also this viewing point C. So we're going to consider this planar region which passes through this line L1 and also passes through C. So to illustrate this, let's draw this line back to C now. So we're thinking of this as a kind of planar region, and it has this line L1 at the bottom, and it's also passing through this viewing point C. Now, this plane is obviously going to be parallel to the line L1, and also it meets C. Now, if we backtrack from C, we can track back along this line, which is parallel to L, but at the same height as C, essentially. And that's going to meet this vanishing line at a point. And a bit of thought will convince you that this point is actually going to be the projection of the very distant points on this line L1. That's where they're going to get projected towards. So, in other words, what we're saying is that the very distant points on this line L1 are going to get projected towards this point, which we're denoting VM, which is on the vanishing line, on the horizon. Now, notice that this point's not the same as the principal vanishing point, which we were discussing before. The principal vanishing point in this picture is essentially the place where this yellow line meets the picture plane perpendicular. So I'll draw it on there as a red spot. So VM here, which I shall draw as a blue spot, is in a sort of different place to that. And in general, lines in the scene which have different angles will meet on different points on the horizon. But parallel lines always meet at some point on the horizon. And this is one of the sort of most important principles of perspective drawing. Okay then, so now what we're going to do is tackle the most fundamental problem behind this projective drawing, which is essentially just that if we have a given point, then where does that particular point end up getting projected to on the picture plane? So we're going to do this analytically using Cartesian coordinates. So let's just suppose that our viewing point here, this point C, we'll suppose that that has the coordinates which are equal to 0 on the x-coordinate, -3 on the y-coordinate, and 2 on the z-coordinate. So in particular now, we have that the scene corresponds to the set of all points which have a z-coordinate equal to 0. So here's the scene, and it basically corresponds to the plane where z equals 0. And also, this picture plane here, this blue plane, this corresponds to the points where y equals 0. So now what we want to do is think about how arbitrary points on this scene are going to get mapped onto the picture plane. What are the images of particular points on the scene going to look like on this canvas? So we'll just do this completely generally. We'll suppose that we have a general point on the scene. And so we can just write such a point, let's draw it here. Or we can just give it the coordinates x, y, 0. So obviously it's on the scene, it has z coordinate equal to 0. And now what we want to do is project this point towards the viewing point C. And we want to find where this ray pierces the picture plane, because that's going to be the image of this point. And we're going to call the image of this point, we're going to call it x dash 0 z dash. So this is basically all we're going to do. We just want to find out how the image x dash 0 z dash depends upon the original point x, y, 0. Okay then, so how are we going to go about determining this image point x dash 0 z dash? Well, the first thing to notice is that it's obviously going to lie on this ray which goes from x, y, 0 to the viewing point C. So we can actually describe that ray with an equation. So in particular, every point on that ray can be expressed in the form x, y, 0 plus lambda times 0 minus 3, 2. Take away x, y, 0. Now, the reason that all the points on this ray from x, y, 0, the object on the scene, to the viewing point C, the reason that they can all be written in this form here is essentially that this equation, what it's saying is that we start from x, y, 0, and then we go lambda in the direction equal to C, take away the coordinates of our object, x, y, 0. So essentially what this is saying is we start at the object and then we travel lambda from the object towards the viewing point. So this obviously is going to correspond to this ray here drawn in blue. And for lambda between 0 and 1, that describes this ray here that I've sketched that goes from the object to the viewing point. We can simplify this expression, so we can rewrite it as x take away lambda x, and y coordinate is y take away lambda times 3 plus y, and the z coordinate is 2 lambda. Okay then, so now the point here is that we want to find the image of x, y, 0. And that is the place where this ray, which is essentially described by this equation here, that is the point where this ray meets the picture plane. Now this picture plane here, this corresponds to the set of points which have the y coordinate equal to 0. So in order to find out where this ray pierces the picture plane, basically we just have to solve this equation and find out when the y coordinate is 0. So essentially we just need to solve the equation y take away lambda of 3 plus y is equal to 0. And that's very easy. And we just get that lambda is equal to y divided by 3 plus y. So now to find out where this ray pierces the picture plane, in other words, to find this point x dash 0 z dash, which is the image of our object, all we have to do is substitute this value of lambda which we've found into this equation which describes the ray. This gives us the particular position on the ray that we're interested in. So if we look at what this is, we find that the answer here is 3x divided by 3 plus y. So that's the x coordinate. And the y coordinate is 0, of course, because it's on the picture plane. And the z coordinate is 2y divided by 3 plus y. And so this is in fact equal to our points x dash 0, z dash, which we have been trying to find. Our essential conclusion here is that when the scene and the picture plane and the viewing point are lined up in this particular configuration, we always have that a point x, y, 0 on the scene is going to get projected to the point 3x divided by 3 plus y, 0, 2y divided by 3 plus y on the picture plane. So essentially this formula tells us exactly how points on the scene appear within the picture. And we can think of this as a kind of transformation rule. Okay, so now we're going to have a look at a problem of perspective drawing, which has a much more interesting solution. And in fact, it gives us a very, very useful tool. I'm not going to say what that is yet, you shall see later on, but it's rather peculiar how a certain kind of object on the scene may look rather different on the picture plane when it's drawn with perspective drawing. So we're going to keep the same setup as before. We shall keep this z equals 0 plane as the scene, and the y equals 0 plane as a picture plane, and the viewing point again as 0, negative 3, 2. So our crucial observation from last time still holds, and that is that a point x, y, 0 on the picture plane gets mapped or gets projected onto a point 3x, 3 plus y, 0, 2y divided by 3 plus y on the picture plane. So we have this kind of transformation rule. So on the scene here we have a parabola, and what we're interested in is what shape is the image of this parabola going to take on the picture plane. Is it also going to be a parabola, or is it going to be something else? Okay, so we'll describe this parabola parametrically. So in particular, the parabola is the set of all points with coordinates of the form t squared 0, where t can be any number, positive or negative. And so in particular, as we kind of vary t from minus infinity to infinity, we sketch out this parabola in this way. Now, as I say, what we're interested in here is how this parabola gets projected onto the scene. And so in order to figure that out, all we have to do is just use our sort of law of projection, which we discovered before. So in particular, all we do is just apply this rule when x is equal to t and y is equal to t squared. And then we're going to get a parametric equation for the curve, which is the image of this parabola. So let's see what happens. Okay, so when we apply these projection rules, we find that this parametric form of our parabola changes into this parametric form here, which is 3t divided by 3 plus t squared, 0, 2t squared, 3 plus t squared. And some of you might recognize what this actually is. It's actually a surprisingly familiar shape. If you draw this curve, which would obviously end up being drawn on the image on the picture plane, if you draw this curve as t varies from minus infinity to infinity, you'll see a very familiar looking shape. So as you can see here, what this curve actually corresponds to is a circle within the picture plane. I mean, we can only see part of it here because we've only got part of the parabola drawn. But as we draw more of a parabola, we see more of this circle shape appearing. And it's really remarkable that we actually get a perfect circle out of this, because we didn't put in anything like that. The parabola is obviously an extremely different shape. Now, in a way, we can sort of see the logic as to why we end up getting a closed shape out of this. And we can see that by thinking about how as this parabola is drawn further and further, in other words, as the absolute value of t becomes larger, these lines essentially become parallel, kind of traveling directly away from the picture plane. And of course, parallel lines will meet at some point on the picture plane. So that sort of implies that this parabola is going to end up making a curve on the picture plane, which actually is like a closed curve which meets at a point at the top. But it's particularly remarkable that this gives us a circle. Now, you might not believe me just by looking at this small picture. So let me show you a more well-developed image of this. So indeed, if we rotate this around, we can see that this parabola is really getting projected onto a perfect circle in the viewing plane. So it's really rather remarkable that, what looks in reality like a parabola can be projected into such a wildly different form as a circle. Now, the relationship here is that both of these are examples of conic curves. Now, I'm going to speak a lot more about that later, because there are some very interesting facts about how conics relate in projective geometry. So, what we've essentially got here is that when we have this parabola, which has equations t squared 0, and we project that towards this viewing point, which has equations 0, minus 3, 2, we get this curve here on the picture plane, which is the plane where y equals 0. And so, in particular, the equation that we get on the picture plane is 3t divided by 3 plus t squared 0, 2t squared divided by 3 plus t squared. And this actually turns out to be I've heard it referred to as a rational parametrization of the circle. It's something which Norman Wildberger discusses in some of his fantastic lectures on mathematics. So, in particular, there's a form like this of producing the circle via a parametric equation, which is very well known. I've never seen this particular result derived before, but I'm sure somebody's happened upon it. But it is well known that you can get a circle by taking a form similar to this and letting t vary from minus infinity to infinity. And the point here is that we're describing a circle without any transcendental functions. We're not invoking the sine function or the cosine function, which are actually remarkably complicated things. I mean, I know we all encounter them when we're teenagers and things, but to be honest, to express them properly, you need infinite series and things like that. These are really remarkably complicated functions. Unlike this approach, where we're really describing a circle just using rational notation and completely closed form stuff, which is very simple. So there's really two remarkable things that were found out here. Firstly, the projection of one shape can look quite different. So the image of this parabola, for example, turns out to be a circle, which is a very, very different shape. And secondly, we have that we've found a way to describe the circle here using only sort of standard rational functions, just quadratics, which is quite a remarkable thing to be able to do.